This is a Professor CBMD PhD, and today's Friday, July 31st, 2026. It is 5:49 and 15 seconds a.m. Eastern Standard Time, and today's research, photonic time crystal. So let's hop to it here. World first photonic time crystal opens a new era of light control. The first all-optical photonic time crystal could unlock ultra-fast computers, adaptable communications, and entirely new kinds of lasers. Date July 31st, 2026. Source: Polytechnic Laboratories. The researchers and scientific investigators have built the first all-optical photonic time crystal, allowing them to reshape the behavior of terahertz light at extraordinary speeds. The breakthrough could open the door to ultra-fast computing, smarter communication systems, advanced imaging, and a new generation of highly tunable lasers. Controlling how light behaves inside materials has already led to technologies that shape modern life. Optical fibers carry information across communication networks. Lasers provide highly precise light sources, and optical sensors are widely used in chemistry and biology. The largely underused part of the electromagnetic spectrum sits between conventional electronics and photonics research, and the field is advancing quickly because terahertz frequencies 1,000 times faster than used for electronic components can offer powerful new ways to examine and manipulate matter. The terahertz range represents the frontier between electronic and photonic technologies. It is a range full of opportunities both for science and for the society. It is still underdeveloped technologically compared to its electrical and photonic counterparts. Creating photonic crystals could lead the way to the closing of this gap. Conventional photonic crystals are nanostructured materials containing a repeating optical pattern, like a lattice, that determines how photons move through them. By carefully arranging materials with different shapes and refractive indexes, scientists can block, guide, or strengthen selected wavelengths of light. In that sense, photonic crystals control photons in a way that resembles how semiconductors control electrons. Earlier experiments by the team showed that temperature and magnetic fields could change the ability of photonic crystals to capture light. However, once those conditions were established, the optical behavior remained fixed over time. The new device goes much further. Its optical properties, e.g., reflectivity, resonance, frequency, can be altered dynamically on picoscale timescales, close to the timescale of light's own oscillations. Rather than relying on only a pattern arranged across space, the photonic time crystal introduces a repeating pattern in time. By extending photonic crystals from space to time, we open a new dimension for light control and advanced path toward amplification and lasing that could be a game changer for optical technologies at terahertz frequencies and beyond. Creating such rapid control required a highly specialized and complex device. The researchers constructed a form of photonic crystal known as a plasmonic metamaterial. The material contains micrometer scale gold, granulated structures positioned above an insulating layer, and a semiconductor made from a mixture of indium and antimony. The gold structures form tiny cavities that confine light between the gold and semiconductor layers. When the semiconductor surface is excited, it produces surface plasmons, collective waves of electrons that can capture light and maintain its oscillations. This interaction gave the researchers a way to manipulate the trapped photons with exceptional speed. The team exposed the device to terahertz laser pulses produced by TLEBE and HZDR's ELBE accelerator. Because the source generates intense terahertz radiation that can be tuned to different frequencies, the researchers were able to change the material's optical properties, especially its reflectivity, both strongly and rapidly. Achieving these two effects at once had been a major technical obstacle. The strength of the change was comparable to forcing an object to emit a completely different color, while the transformation occurred on the picosecond scale, 1/1000th of a second. TELBE, unique ability to generate high field phase stable terahertz pulses, was critical. Without this infrastructure, achieving the coherent ultra-fast modulation needed for the PTC regime would have been impossible. The calculations also showed that changing the material over time cut photon dissipation in half. In this context, dissipation refers to the portion of photons that are not reflected and instead pass through the metamaterial surface. The theory not only reproduces the experiment but also provides a basis for guiding future discoveries in this system. The researchers now want to reduce photon dissipation even further and increase the number of photons held within the crystal. If they can produce sufficiently strong amplification, the device could become the basis for highly adaptable new lasers. Photonic time crystals could ultimately change how light is used in technology, especially within the terahertz range. Their ability to alter light on extremely short timescales could support ultra-fast lasers for medical imaging and communications. The technology may also make it possible to tune properties such as light's color or intensity almost instantly and on demand. The level of control could lead to faster, smarter, and more adaptable optical systems. And this videography was created for educational purposes only. My code name is Will. I'm Professor Christopher Brunet, leader of research scientist, ufologist, psychic, computer technician, computer programmer, philanthropist, writer, mathematician, artist, photographer, film producer, chef, animal, and nature lover. My passion is world peace. Have a great day. This is a Professor, CBMD, PhD, and today's Friday, July 31st, 2000.